So good evening, everybody. Welcome to what we're calling lesson 3. We're about halfway through. Basically, the next 2 lessons after tonight will be additional things for you to do and build. Tonight will be more on simulations and physics and theory. And then there will be checkouts and then we'll fly. So got to keep up. Here we go. The plan for tonight, as sort of as usual, I'm going to take a quick look at some homework and vocabulary pages. They're pretty short. And then turn it over to Kelly to talk a little bit about what she's been up to. Maybe she's done. If she's not done, she's going to tell you where she's headed and show you what she's gotten to. And hopefully you're following along, maybe closely along. That would be good in her build progress and your build progress. Our hope is that by about this time next week, you will be done building. That's not quite true because next week we're going to have you build a whole new thing. But the main airframe, the main structure, hopefully will be well along, if not finished by this time next week, so that you can take the last 2 weeks to do the electronics and do the painting and not knock yourself out. Here we go, share screen. So this is what's been 5 things, I guess, and those 5 things includes some slides I'll go through. The rocket motion slides, you'll see those in a moment. Includes 2 models. Kelly might show us a third. We might post a third model. We'll work on a model from scratch, in fact, later. So I can't really open those up in this format anyway. But let's take a look at the vocabulary and the homework. And let's see if I can get some people into the room here. One moment. We got to notice that there are people in the waiting room, but I'm not sure how to get them in. There we go.
Is that who I'm? Dorothea, can you put your school name behind your name?
Yep.
Same with you, Jonathan, if you could put your school name behind your name.
Okay, so this is it as far as vocabulary / concepts. You've heard many of these things before. You need to protect your parachute one way or another. So I gave you 2 flame protectors. On the other hand, I also gave you parts for a piston, and Kelly is building a piston rocket just to show that she knows how to do that. I think that might be, Kelly, the first piston rocket for you?
Yeah, it actually is. So I thought
That's
I'd
good.
try something that I haven't done before because somebody else is paying for it.
Absolutely, that's always good. So we used rocket barf, that cellulose stuff, for the model rocket. Typically, you don't use that for high power. It's just not good enough for the explosions we're going to be doing in these bigger rockets. You want to pull out your drogue if you have 2 parachutes, your drogue at apogee, essentially. That allows you to come down pretty fast, but at least not drift sideways too much. And then sense that ground is coming up and open a main so as to land at a more appropriate speed. So the main purpose of dual deploy is to limit lateral drifting in the wind. I remember teaching a freshman seminar where students wanted to build a really big rocket, and I said, okay. And so they built a really big rocket, and I gave them a 12-foot parachute. Literally, I just had one sitting around, and they pulled it at 5,000 feet up. They were not supposed to. They pulled their main instead of their drogue, and they had a 1.5 mile walk to get their rocket back. On the other end, it was 12 feet. We could see it really easily. Later in this lesson, we're going to talk about doing simulations. The book, the model rocketry book, talks about simulations. The high power rocketry book doesn't. Not because it's not important, but because they assume if you're into high power, you already know about simulations, having gotten there from model rocketry. So anyway, the 2 simulation programs I'll mention, but I will only use one, are RockSim. That's the one that's talked about in the book, and OpenRocket. And I will use OpenRocket, frankly, because it's free. $100 or so. It used to be, at least for RockSim. It's only slightly cooler. OpenRocket does as well as far as the theory, and RockSim has a few small features that are extra, but in my case, not worth the money.
Except at supersonic speeds.
Well, it's true. Different simulation programs handle certain things, specialty things like supersonic differently, and it's possible. Maybe Kelly sounds like she knows this. I didn't realize this. Maybe Open Rocket is not that great if you're trying to go supersonic. We are not. With this kit rocket and the motor selected, we are not going supersonic. But if you're going supersonic, maybe you should be a little more careful than we're going to be. You'll notice in simulations, there will be a list of parts, some sort of a parts tree, and some parts will be considered parent to or child to other parts. That will become obvious when we get there. You'll also notice I'm going to show you a rocket that's fundamentally unstable, and I'll take a crack at fixing it by adding ballast. So frankly, the rocket will become heavier, and so it won't fly as high, but at least it will fly in the right direction. So if you have an unstable rocket, it won't really fly at all. It'll just tumble. So sometimes adding ballast will make the rocket fly much better, even though you think adding weight doesn't sound like a good idea, but it has to be a stable rocket. On the other hand, you have to be careful. The simulations will tell you what they believe the stability to be, but you always need to balance the rocket in your fingers after you build it, if it's small enough to do that, and make sure that the simulations are just not leading you astray. We'll show some plotting and how the simulation programs often plot many things on top of one another, which can be a little confusing. I often tell students, don't try this in a class. Your professor will not like it, but this is how the simulation programs give us the data. You need to be able to read these graphs. I just encourage you, don't necessarily do the same thing when you're generating graphs yourself if you have the choice. It turns out that rockets have a tendency to pivot about the center of mass, but what's making them pivot is the air forces, which are acting mostly on the fins. And so essentially you need the center of pressure, the center of air force, lateral air force, to be behind, to be aft of the center of mass. And what happens is if there's a sideways wind, so most of the wind that a rocket sees is the fact that it's going through the air very quickly. But if there is a sideways wind, the rocket will have a tendency to tilt into the wind. That's called weathercocking or wind cocking. Sometimes that can be quite severe if it's a very strong sideways wind. And this can actually lead your rocket to be going essentially horizontally too early, like before the motor is done burning sometimes. And that's usually a really bad thing, because when the motor, when it reaches a horizontal state and is not going up anymore, you might have electronics on board that say now's the time for parachutes. And if you're going horizontal at a very high speed, parachutes are not a good idea. So we'll talk a little bit about that. The motor that we're using burns pretty quickly, and therefore you won't really have time to tip all the way over, as long as you get the thing off the rail at a reasonable speed so it can self-stabilize it.
You know, I actually have a flame shield right in front of me here that it ejected at 1,000 feet per second velocity, and it barely survived. It ripped the whole outer diameter of this thing apart. You can imagine this is really, 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 really strong. You can imagine what happened to the parachute.
I suspect the parachute is not in as good shape as that.
Not even, it's in multiple pieces though.
Okay, fair enough. Not a good idea to pull parachutes when you're traveling at high speeds. We're going to try and pull one parachute at apogee when you're hopefully not traveling fast at all, maybe even zero, although you're almost always tipped over and going sideways a little bit. And then pull our second parachute before we reach the ground, but make sure that the drogue parachute is at least big enough to give us a chance to get the main out without breaking something.
Hey, Professor Flaten.
Go ahead.
I imagine if a rocket is traveling horizontally at high speeds, that is a bad thing. And it also might end up hitting the ground at a high speed, which would be a bad thing. Like, wouldn't deploying a rocket, even if it's not, or deploying a parachute, even if it's not intentional, like, wouldn't anything to get it to slow down and not hurt people and land more gently be a positive?
Okay, that's looking at the glass half full instead of half empty or something like that. But okay, what's going to happen is you're traveling sideways. You shouldn't be traveling sideways at high speeds. That's called a missile, not a rocket. But if it happens, it's true. What does NASA do if their rockets are not rockets but missiles? They send a self-destruct command. And that's kind of what pulling a parachute does, is it makes the rocket blow up or into pieces. And so I guess it's true. The big pieces maybe don't hit the ground, or the spearhead pieces don't hit the ground, but then all the shards hit the ground. And so it's kind of which of the two do you want to, deal with? So the best thing is just don't go there if you possibly can help it.
Yeah, we had a motor failure where the motor kicked out. It turned over like it was at apogee, and then the motor started burning again. When it hit the ground, motor started up at maybe 400 or 500 feet. When it hit the ground, it buried the nose cone about 8 inches in the ground, and it shortened the rocket by about a foot. So you always want to try to keep these things pointed up.
On the other hand, if you don't manage to get a parachute out, it will come down gravitationally at a very high speed, and we call that a lawn dart. I remember one lawn dart that literally disappeared underground, but there was a beeper on it, and we found it by going around the ground and looking for what part of the ground was beeping. That was impressive. We got the rocket back. It was not in good shape, but we dug it out. It was fully underground.
We found 7 pieces of one of these, and we only recovered half of it. So that gives you an idea of the kinetic forces. That's why they tell you to never try to catch a rocket coming down also, because it can hurt you quite bad.
Okay, pressing on, and then I'm going to turn this over to Kelly to give us an update, and then I'm going to do some theory. So here we go. For reading, there's several chapters in the High Power Rocketry book I want you to look at, and also chapter 21 in the Model Rocketry book. That's the chapter on simulations, although it's not Open Rocket, but RockSim. It's similar. For exercises, I'm going to show you some rocket motion slides very quickly. I would encourage you to spend more time than I do tonight looking those over. And then get a copy of Open Rocket, download it, get some people on your team, maybe more than one, to practice using it. And we're going to develop the beginnings of a model, in this case, a simulation model of your rocket. And then you need to take the beginnings of that model, and the homework more or less for this week is going to be take that model and make it look like your real rocket and show us in about a week's time how it's going. We will be flying with a Cicerone H225 motor, and so that's the motor we'll be putting into our simulations. As far as build, you should be building your airframe, and we're going to start building the AV bay next week, so it would really be nice if the airframe essentially was done, if possible, or close to done at least, before next week. That's all I got as far as homework and vocabulary concepts, so that was actually very quick. And I'm going to stop sharing and turn this over to Kelly for an update, build update.
Have you, is screen sharing enabled for me?
Here's what I'll do. I will spotlight you.
Okay. I need you to turn on screen sharing so I can show them that Open Sim or the Open Rocket.
Oh, if you click on screen sharing, it doesn't let you?
Yeah, it's disabled by you. You have to enable it.
That's bad because I don't remember how to do that. Anybody?
It should be on the little taskbar down there. When you go down, there should be a little chevron that you click, and it says enable screen sharing for all participants.
I'm looking. Okay, try now.
Okay, there we go.
My other account is set up to always let people screen share, so I'd even forgotten how to do that. Thank you.
Okay, so this right here, real quick, is what you're going to see when you see Open Rocket. You'll notice that down here it says Mach 1.12, but we had flown at Mach 1.77. The reason behind that is because this little question or this exclamation point here will say, body calculations may not be entirely accurate at supersonic speeds. So if you are flying something supersonic, you have to take it with a grain of salt on this particular program. So what you're going to have is you're going to have these different body pieces here that you're going to be able to do different little things with. You're going to be able to make transitions or body tubes, nose cones, couplers, etc. And you're going to be able to take all of these. For instance, with the avionics bay, I started with a switch band right here, and ignore the fiberglass. We're not using it. This is our fiberglass build. So some of the things are going to be quite different than what you see. I started with a 1-inch fiberglass switch band, which is a body tube. And then inside of that, I put the coupler, which is right here. So the switch band is the overall thing, and the coupler is below that. And then there's the ejection charge holders and the steel eye bolts, the terminal blocks. Everything goes in this where you would expect to see it on the rocket itself. A couple things of note are inside of the lower body tube, you're going to pick not fiberglass, but motor mount. And that's actually going to have its own particular categories in here. So when you go into that, it's going to ask, is this component a motor mount? And that's where you're going to click it right here to make sure you've got that. So it's just a standard piece, but once you click that coupler and turn it into that, it makes it a lot easier to figure out what's going on. And then in there, you'll see that there's also a motor retainer at the back end, not our little washers, a little different. And the last thing in here that I kind of want to do an overview for you is the fin, how you design the fins. So you're going to come into this menu after selecting fins right here, and you're going to put the number of fins. Don't worry about rotation. It'll put them at every 120 degrees. If you did pick a rotation, you'll see down in the picture down there that it rotates them. Not really important. It's not going to literally change anything for you. Where you're really going to see a lot of this stuff is in your thickness of your fins, in the fillet of your fins, what material you're using, and whether you rounded it, squared it, or had an airfoil on the front of your fins. And the last thing you're going to see in this program is going to be where you actually design your fin. So that's going to be important. You're going to need to get not the root edge, but the root edge of the exposed part of the fin. You're going to need to find out where that starts, where that ends, and kind of the XY coordinates of all of the parts. You'll see them over here. I had this in millimeters because the kit was in millimeters. So you'll see that there's slight variations, but typically it's 6, 3.7. And that's how you're going to track your fins. When you go over to the third tab here, fin tabs, this is where you're going to change the length of your fin tab and how tall they are inside of the body. So you're really going to just do the top 3 here. You're going to put in your general information about numbers. You're going to shape it out. And then you're going to put the depth of your fin tabs and how long it is. Don't use this information here, obviously, because there is no correlation between this beyond 3 fins and what we're using. There's a lot of differences here. But this is essentially, if you're going all out, this is essentially what you'll get. You'll get a motor tube, you'll get the motor mount tube, the retainer, couple, well, in our case, there's going to be 3 of these centering rings. Fins, you'll get your parachutes with your cords, your nose cone, upper body tube, lower body tube, and all of your avionics based stuff. So that's what we've got going on there. Let me get back over and stop sharing that. So
that's very, let me just make a quick comment. That's very impressive. Turns out that we're going to do less. You can do all that if you want to, but we're going to allow you to do less. You just have to capture the essence. So in other words, there is a coupler and it's got avionics and it is about 6 ounces. That's good enough. You don't have to necessarily draw out every single piece inside of the avionics bay, but by all means, you certainly could. And if you did so, it would be a better model still.
I forgot to show one more thing. Right here, if you look closely, you'll see what looks like a BMW logo. That is your center of gravity. That is typically where you want to put your rail button, your upper rail button. Your lower one you want back here, but out of the way of the aft centering ring. And your front one you want right here, slightly in front of that. So that's what this is really going to be really good for, is figuring out exactly where we need to put that rail button. So you'll see I don't have mine on yet because I haven't finished all of my calculations in here for our current model. So just keep that in mind. You're not going to put that on until you have a good model. As far as the build has been progressing, what we end up having right now is, if you've made it to the end of the slideshow, you're going to have your 3 fins in. They should be filleted. You're going to have your rail button, and you're going to have your back centering ring. I haven't put any fillets in here yet. I plan on using the JB weld in here as a heat material. But you'll also notice that my standoffs, I went ahead and got some aluminum for the standoffs. So when I said to measure an extra 9 millimeters here, what that 9 millimeters is basically where my finger is. That's going to be this little part right here, that little black band. You don't have that. This is a spent 225 cartridge, and that's 9 millimeters thick. So when that's slotted in there, it makes up that difference. So that's part of the calculation you're going to need to do. So you really want to start to get these fins knocked out. You want to get the fillets in there. This white stuff here is just to make it so there are no, wrapping bands. I like to have smooth on there. And you're also going to want to make sure you've got your knot on. Oh, that's swinging a lot. Your approved knot on the end, maybe a quick link going on there. you're going to want to have your nose cone done with the eyelet in there. You can cover that back up if you want, but some people are going to put some things inside of here. So if that's the case, you're also going to need to drill a hole in here to make sure that the pressure is equalized between outside and inside. So you can leave this open for that reason. You'll have to tape over this in flight so that all your stuff doesn't fall out. And that would be a good place to be settled right there. Avionics bay, you really don't have to have the internals done at all for the avionics bay, but you are expected to have your 2 blocks done. Not this though. You can if you want to. That's going to be where our ejection charge goes. But you are expected to have the eye bolts done with the 2 all threads going through, and you're going to want to have those in here. You're going to want to have them locked down so that the threads are basically tied to one cap completely. And I'm going to take this off so you can see what that looks like by itself. The other end is going to be connected with wing nuts. So you can just, hand tighten those and you can put the other face on. So essentially what you're looking at is you're looking at this as your whole rail. Ignore these wing nuts. I'm using those to shorten my board slightly so it doesn't jostle around in there. We'll get to that later. But you're going to want to have one of these, and you're going to want to have one of these. You'll also notice, you might have quickly noticed, that I went through the whole thing with the bolt there and the nut. I've had some bad experiences where these things have jumped right off of the bulk plates, and I don't enjoy that. So I bolt them straight through now. You will want to have your board itself done, but not the electronics on the board. So you're going to want to make sure that you have something where both of your sets of holes will go all the way through. If you notice, like I was saying, I'm limiting this. If you look under here, it sits right up against those 2 wing nuts. And I use wing nuts because they're a lot easier for me to control the depth on those. The front end of this, when you put the other cap on, you can see it sits real nicely in there. And then I don't have to do anything. That's the exact length of my avionics bay. You'll also notice that I am using my own custom 3D printed battery holder as opposed to the one that's given to you. However, one thing that is consistent about these is the position of the battery. When this is accelerating, that battery will be forced downwards. And so both of the terminals will stay in contact with the 9-volt. They won't separate out. So make sure you're doing that. And one of the last parts that I have that I've been working on, well, 2 of the last parts. One, I've got my piston, and you guys may have this all worked out, but I've also gone ahead and done my quick links for my parachute and for the nose cone and going down to the avionics. So it's kind of a whole string. Kind of hard to get this into one picture here.
How did you get so many quick links? I didn't give anybody else that many quick links.
No, you didn't. I went and bought some of my own stuff. I like creating a little piece of art out of these things.
Okay.
And another thing that you will see is like I said, you have to equalize the pressure. So I've got a hole in my upper body tube that is going to not interfere with where my nose cone sits. And that way I can drape some things from my nose cone into the body tube and they will equalize through there. On the bottom, those are the rivets. You might have been wondering what the rivets are going to be like. They are locking my lower tube right now, or my upper tube with my avionics band. So this is the switch band. This is the avionics tube, and they're just riveted nicely in there. You can kind of see that rivet down there. So these don't need to come apart at all. And that means that the side of the avionics bulk plate that's locked up is going to go up in there. So when you have that tied up and you flip this over, you can unwing nut this end and pull everything out from the exposed end while keeping this all locked up into one unit. And that's pretty much where I am right now.
So that's impressive. It turns out that I would consider the coupler tube, the end plates on the coupler tube, and the threaded rod that goes through to hold the top to the bottom all as airframe structural. On the other hand, the sled and the electronics that go on the sled, we will talk in much more detail, in fact, about that next week. And so Kelly's giving you a heads up. I sent you a piece of wood that you could use for a sled. You don't have to. On the other hand, it won't work as I sent it to you. And the reason is it's rectangular. And Kelly, can you show the fact that you had to notch out the ends of your sled?
Sure can. So if you look at the ends here, if you look at the ends, you can see that they have little notches that are going to fit directly with the bolts. So
that bolt will interfere with the sled. You'll have to fix one or both of those things to make them fit together properly. But I gave you something that you could make a sled out of. We will talk about sleds, both mechanical and electrical, next time. We would like the airframe, which is the parts, the end plates, and the threaded rod to connect the end plates to each other. We'd like that all done for sure. And maybe even some thinking about, but perhaps not too much progress on the sled and the avionics until after we talk next week.
So I've just gone ahead while you've been talking, and I put the other end on, so you can see that the wing nut side is always going to be exposed. And when you've got your, oh, that just kind of launched out of there. When you've got your rocket seated together, you're going to have this locked up on this side, but on the bottom, you will have access to the wing nut side of things, which will allow you to gain access if you need to your electronics bay. So this end doesn't need access because it's all locked up. So just remember which end, you want the wing nuts on the side you're going to access. So don't put that on the side that you rivet.
We'll talk more about rivets and also shear pins again at a later lesson. One thing that was a little hard to follow, Kelly, is we couldn't see the nose cone, nor could we see the fin. So it was a little hard to tell what was the top and what was the bottom of the rocket. You have riveted your coupler tube. You've riveted it to the upper section. So the lower section with the fins comes off, and the upper section stays together with the coupler tube has to go somewhere. And in your case, and in everybody's case, it's going to be the coupler tube goes with the upper section. That's our plan. Super. Thank you. Okay, so that was quick, and basically Kelly's got lots of slides to document all of those parts, but sometimes it's good to see them in actuality in person as well.
Hey, Kelly.
So, go ahead.
Why your little copper cup was your charge holder, right? I was expecting that to be on the nose cone side and not the fin side.
It's on both.
We'll do both. We're actually going we're going to fire an explosion at apogee and use the motor as a backup. We're going to try and get the parachute out ourselves and only use the motor as a backup in case we fail what we're trying to do.
Gotcha. Thank you.
Give me 1 second and I'm going to pop these rivets out, and then I'll show you how both ends relate to each other real quick.
Okay, so while Kelly is pulling the rivets, let me just clarify one thing. The rivets mean that it stays together in flight. But what she's doing right now is actually important. You do need to access the upper end of your av bay, and the reason is there's an ejection charge to put in there. You have to be able to reach it so you can place that ejection charge properly. So the rivets go on for flight, but prior to flight, you will have the removable avionics bay so you can work on both ends of it before you fly.
So there's the charge, the ejection charge holder on the side that's locked up. And then there's the ejection charge holder on the side that you're able to open up. So yeah, you'll have both. The locked up side goes up, and that's going to be by itself. So that one definitely has to fire off. The bottom one is just a backup, as Dr. Flaten was saying, for the motor ejection. The motor ejection.
I would describe it the other way, Kelly. We're going to do it. The motor is going to back us up. We're not backing the motor up. The motor will go off for sure.
Oh, fair enough.
We want our thing to go off, and we'll let the motor back us up if we need a backup.
You definitely want to hear crump when you have that apogee release.
Any other questions right now?
Steve, I'm answering your question already. Give me just a moment.
Okay, so here's what we're going to do for the rest of this evening. I want to spend 15 minutes or less, actually maybe less, showing you some theory, and then 15 minutes or less showing you some open rocket. So let's start with a little bit of theory here. Share screen. I want you to spend some time with these slides. But let me just step through at least some of them right now, just to give you a sense for how this is going to go. This is essentially just standard physics, but it turns out the physics is not so standard. And you'll understand what I mean by that in a moment. We're going to do some thinking about and calculating motion associated with a rocket for a purely vertical flight. So that's already in itself not full reality there. Phase one is the boost phase while the motor's firing. Phase two is the coast phase while the motor's not firing, but you're still going up, and then you eventually reach apogee. And then phase three will be the descent phase. This is the easiest of the three. In fact, you are coming down, maybe at some sort of a constant or terminal velocity. So let's just define some things. If up is positive and x is position or height and v is velocity, positive would be velocity upwards, a is acceleration, t is time. And if you happen to have constant acceleration, which we don't, but if you happen to have constant acceleration, you probably already know from a physics class that you can calculate your velocity at any time based on how fast were you going at the beginning time times 0, and then acceleration times time. And you could calculate your position at any time based on where you were at the beginning time, how fast you were going at the beginning time times t, plus 1/2 a acceleration times t squared, where in this case t is the elapsed time. This hopefully is familiar. However, rockets don't move with constant acceleration, so there will be limited utility to these equations, unfortunately. Remember they're Newton's laws, and Newton's laws say that forces can be used to explain motion. And if you add all the forces together as vectors, you can explain the acceleration as long as you know the mass. So here are the three diagrams. Basically, for the first diagram, there should be a really big thrust vector. The figure is a little misleading. The thrust vector should be very long, and then the weight is downwards. That's gravitational weight. Drag resists motion, so that's along the length of the rocket in the backwards direction. And then any sideways forces, which I'm going to neglect. I'm going to say this is pure vertical motion with no sideways forces, so they would technically be called lift, but I'm not going to go there. During the phase two, it looks exactly the same, except there's no thrust. And it turns out there's a little bit less weight because you've burned away some of your motor. Your propellant is gone now. And then in phase three, you're coming down. And so this is completely different. You have a parachute, which is producing the drag with an upwards force because the motion is now downwards. And then there's the downwards weight, which is constant. That's the burned out weight of the rocket, as opposed to the full loaded weight when you launch it. So here's definitions. I need to turn something off on my screen. It's blocking my view. One moment. Hide video, hide floating meeting controls. There we go. Okay. So I already sort of defined those things. Spend some more time with these slides, please. Let's just take a look at Newton's laws. Newton's first law just says that if the forces happen to be balanced, your velocity will be constant. And Newton's second law says if the forces are unbalanced, then you can figure out your acceleration by adding the forces together, dividing by the mass, and that will give you your acceleration. It turns out that that's not what Newton said. Newton actually said changes in momentum are explained by the sum of forces. And so this F equals ma, or sum of F divided by m is equal to a, really only applies if m happens to be constant. But Newton's had a sort of a bigger version of that, and his was sort of more appropriate in some sense. But this is what's usually introduced in a basic physics class. Here we have changing mass, as well as changing force, as well as changing velocity, as well as changing drag. It's very complicated. Newton's third law just says when objects interact, both of them get forced in opposite directions. That's important, of course, but not so much for the calculations we're going to do. Let's look at the third phase, because this is by far the easiest one, okay? So in this case, the drag upwards force actually will equal the weight downwards force, so you will travel at a constant speed, a constant velocity downwards in this case, called the terminal velocity. Here's how you might draw a free body diagram with two forces in two different directions. The acceleration is 0. You're not changing your speed. The mass is the burned out mass, shall we say. And the weight is related to g as W weight equals m times g. And the drag force is related to a few things. in this case, it's related to the density of the air. It's related to the velocity, the terminal velocity, and it's related to the area of the parachute. That's what's causing the drag, as well as a coefficient, a drag coefficient. So I'm calling that C sub D, drag coefficient, coefficient D, drag. But then I say P, and the P just means this is a parachute, because later there's going to be a coefficient of drag associated with a rocket. And so in this particular case, V is the terminal velocity, A is the parachute frontal area, and C sub D is typically between 1 and 3. It depends to some degree on the shape of the parachute. And then, of course, the area of the parachute is also important. Density for air is known, and we're not going so high that that density will change very much, at least on these flights. You're going to apply Newton's laws. And in this case, since things actually balance, you can either solve for the terminal velocity, if you happen to know things about the parachute, or you can say, I want a specific terminal velocity and solve for the parachute. In other words, you can use this kind of calculation to choose what's an appropriate parachute size. So you can go either way. If you have a parachute, you can figure out how fast you'll go, or if you have an idea of how fast you want to go, you can use it to figure out what kind of parachute you should choose. Good news, all of this stuff will be done by the simulation programs for you, but I think it's useful to have some sense of what's going on behind the scenes. Let's look at phase 2. This is more complicated. So now we're going up, but we're slowing down because of gravity, and there's no thrust. This is the coasting phase. Drag is not constant because the speed is changing. Weight is constant. We're at the burned out weight. So here are two forces, both of them act down, so clearly we're accelerating down. And weight is the same, and drag is the same, except in this case, it will depend on your velocity, which will be changing. You're slowing down, and it will depend on the cross-sectional area of the rocket, AR, and the coefficient of drag for the rocket, CDR. And if it's a streamlined rocket, you might hope that some of these things are pretty small. So you might even dare ignore the drag. It's not a good idea, but that's about the only way you can make much progress in actuality. Certainly not a constant acceleration situation, because the drag is changing unless you decide to ignore it. Okay, so here's how Newton's second law would lay out. And as I just mentioned, the drag is perhaps going to be small, and it will definitely be small once you start going slow. But it turns out that when you're going really fast at your top speeds, the drag is not small. It might even exceed the weight of the rocket. And so if you ignore the drag, you can do things like say, oh, this is just projectile motion of like a vertical ball or something thrown up, right? And you can say, I can figure out how high it's going to get, or how long it's going to take to get to as high a point. But notice that this is from the end of the burn to apogee, not the beginning of the flight. So the bottom point in time and the bottom point in position is not the ground level. It's where were you when you finished burning, which is the end of phase 1. So you need phase 1 to know what is the input numbers to put into phase 2. Okay, but you can actually calculate how long you might coast if you ignore drag, and how high you might get from burnout to apogee. Phase 1, this is the worst one. Okay, so in phase 1, you have a very long or very big thrust. The thrust actually should exceed the weight by a factor of 3 at least, and possibly more than that, to make sure you get off the rail fast enough. So in this case, the acceleration is definitely up. Thrust will win over weight, which is diminishing as you burn fuel, and drag, which is increasing as you go faster and faster. And then thrust itself is not going to be constant either. There just is not any motor that burns with a constant thrust. It doesn't exist, only in your mind. Okay, so thrust is not constant, and the mass is changing, and the weight is changing because the mass is changing, and the drag is changing because the speed is changing, and many, many, many things are changing. And so absolutely not constant motion. You can try to apply Newton's laws, but you won't get very far unless you apply them little bit by little bit, as in for a millisecond plus a millisecond plus a millisecond. Then you maybe make some progress. That's kind of how the simulation programs do it. It's very hard to capture this thing in a grand scheme as you might be able to do if it was constant acceleration motion. So I'm going to skip the next slide and go straight to a thrust curve. This is a fairly typical thrust curve for an H125 motor. We're going to fly on an H225 motor. You can look up the thrust curve if you want. You'll notice that, can you see my cursor?
You'll actually see the thrust curve too in OpenSim.
Yeah, but can you see my cursor?
Yeah, definitely.
Very good. So notice that there's a spike early on. That's associated with how Cicerone likes their motors. And then the motor backs off a little bit, and then it has an area where it's thrusting more and more and more as time goes on, and then thrusting less and less and less as time goes on, and then it dies out. Okay? So here's the maximum thrust. We'll call the beginning of the thrust time or the start time for the motor 5% of maximum, as opposed to the very, very, very beginning. Similarly, burnout will be considered 5% of maximum. And so the duration of the burn is from just after 0 seconds to just after 2 seconds in this case. There's an average thrust. Basically, the thrust goes up and down, and so you can average that if you want to. And so the area under the curve, which frankly would be calculated with the weird curve or else using the average thrust and the burn time, that is the area, that's referred to as the impulse. And motors are classified by impulse. That initial spike, not all motors will have that. Cicerone motors often do. There's a progressive part, a regressive part of the burn. And if it had been flat, we would have called it a neutral motor, neutral burn. Here are the impulse classes. And so we're flying on an H motor, but H and I are the motors associated with level 1 certification, JKL, level 2 certification, etc. The H125 motor, it's got all these details in the name. Cicerone is who makes it. Pro 38 millimeter diameter motor, 266 impulse. So notice impulse comes in Newton seconds, and the H class goes from 160 to 320, and 266 is kind of in the middle there. Okay, H is another much coarser version of what is the impulse. So H is a big range, and 266 is exactly where you are in the range. And then here's the average thrust in newtons. That would come from that previous figure. And the delay time. This is how long it will be from the end of the burn up until the explosion goes off. And you can adjust that from 12 seconds to be shorter than that as you want to. One thing that's missing from this label is how long does it actually burn for. It's about 2 seconds, but that's not in the label. I'm going to skip the rocket equation, and I'm going to skip these graphs and just go straight to here and say, often, too often, things like RockSim or OpenRocket will draw velocity and position, vertical position, and acceleration all on the same graph with multiple labels on the vertical axes. This can be confusing. We're going to see one of these in a minute, so I'm not going to spend more time. Just heads up, you need to be able to read graphs of this sort, and we'll look at one in a second. Okay, here's what I want to do now. I want to spend essentially the rest of our time together tonight looking at OpenRocket. So I'm going to open up OpenRocket. Hello. And when you open it up, it just opens with a blank screen. And Kelly already showed you what one OpenRocket model looked like. I'm going to open.
Could you, when you open it up, could you show them the motor curve in there, how to access that?
I don't know how to access it myself in OpenRocket. Can you tell me?
Yeah, sure. Open that up, and then once you go into motors and configurations,
Okay.
when you go to selecting a motor right there, you have no motor in there. So down where it says no motors.
Yep.
No, yep. Select a motor for that one.
Sure.
And then when you go in, you're going to be given a huge range. The easiest way to do this is on the right-hand side, where it says total impulse, narrow that down left and right just to H.
I'm just going to type H225, and well, that will tell me exactly what I want.
So when you double click on that and you click show detail up, no, go back in there. And you go to show detail up in the upper right.
Ah, never seen that before. Okay.
And there's
Cool.
your thrust curve.
Ah, very good. I didn't realize it was built in. That's nice. Presumably there's a library that has this and all the other motors. And so you can get a sense for the thrust curve. And in this case, there's a little bit of a spike at the end, oddly enough, as well as a spike at the beginning, and a fairly neutral, but not completely neutral curve in the middle. Thank you. I did not know that. Okay. I just want to point out this is a Hawk, and make sure that you are in imperial units. So under here, if you go to File, Edit Preferences, Units, Default Imperial. Not that I love imperial units or US customary units, but all of the rules of thumb, like you need to be going 45 feet per second off the rail. It's not some number of meters per second. It's 45 feet per second. So all the rules that you need to follow are all in imperial units. And so I would suggest doing your simulations in imperial units.
You don't want
If I
13.
look here, I noticed that there's a particular mass for this rocket. And then over here, this is very important. It tells me stability, and the stability is negative. So this rocket is unstable fundamentally. That's bad. Were you going to say something, Kelly?
I was just going to say you don't want to fly at 13.7 meters per second.
I do not. Okay, so here we go. I'm only going to do one thing with this model, and that is I'm going to fix that stability just by adding some weight to the nose cone. Right now, here is the center of gravity, and here is the center of pressure, which is even forward of the center of gravity, and hence the stability is negative 1.11. Okay,
Just
so
as
I'm
a
going to go to rocket design.
just as a
Nose
reminder, the
cone.
body tube thickness is your static margin.
I'm sorry, what was that?
The body tube thickness is your static margin. So when you see negative 1.11, that's negative 1 and 11 hundredths of a body tube thickness.
That's true. So we're measuring just the distance between these two things in body diameters. Okay. So what I'm doing is I'm going to the nose cone and I'm going to say, I just need to add a mass component, a mass object. And as I increase the mass, notice that it moves the center of mass. So right now the center of mass has been moved to be on top of the center of pressure. And if I keep going, I can eventually get the center of mass to be forward of the center of pressure. And now I have a stability of 1.1. That's much healthier, but it took a full pound of mass to make that work. And notice that drew the mass way up here, which is probably unrealistic. I can't actually get 1 full pound in the tip of the nose cone. And so I probably should move it at least inside the nose cone, at least, just to be more realistic. And so I lost ground a little bit. But this is what Open Rocket, for instance, can allow you to do, is study issues of stability even before you build the rocket and just say, okay, I guess I better be ready for, or I better modify, make something bigger, make something heavier. In this case, you absolutely need to add mass to the nose cone. Otherwise, this rocket will tumble. It will not fly up at all. So it's an unusual rocket in that it's sold as a kit, but this kit is fundamentally unstable. You got to watch out for that. Our kit will not have this problem.
May I add one point that is really important?
Please.
So if you're going with stability, let's say you get a nice, cool 1 stability, 1 static margin. That's not good enough. The reason 1 isn't good enough is because when that motor starts burning down, then you're going to start to change your center of gravity again, and it's going to go under stability. So you need to make sure that you're aiming for somewhere around like 1.2 at a minimum and somewhere around 3 or 3.5 at a maximum, in order not to weathercock or to get oscillations from having a non-valid static margin.
It's good advice. This is what is the stability at the moment of launch when the motor is full. But yes, the motor does get lighter, and that can change things. And sometimes it even changes things in your favor, especially if it's a hybrid motor. But for these solid motors, they get lighter, and usually you lose ground on stability. So anything positive is considered stable. Negative is unstable. Positive is stable, but less than 1, between 0 and 1, that's marginally stable. And if you start at 1, you're going to drift into the marginally stable area pretty quickly as you burn. Notice right now with no motor in, the stability looks pretty healthy, 1.88. But as soon as I put in the motor, then it is less than 1 now. And the reason is the motor adds quite a bit of weight to the tail end of the rocket. That's typical. So here's what we're going to do right now. We are going to start from scratch. So I'm going to say File, New. We're going to draw your rocket. Except I'm not going to actually draw your rocket. I'm going to draw something that looks a little bit like your rocket. And you need to take what I'm going to draw right now. I'm going to call this the preliminary or the draft version. And you need to make it actually your rocket by putting in the right weights and putting in the right lengths and the right, et cetera, et cetera. And I won't even get into all the parts because I only have 5 minutes. So here we go. Let me start to build a rocket from the top down. So nose cone. Our rocket is a 3-inch diameter rocket. And so I'm going to go into a database and see if I can find myself here as outer diameter. I'm going to sort by outer diameter and find myself, I guess they call it, there it is, a 3-inch diameter plastic nose cone. You know, I think I might go with a PML 3.1 inch. It's really the same thing. Different companies do or don't give you that last digit. So if I choose that nose cone, notice there it is. It's got a shoulder. That looks pretty familiar. It's unstable by itself. That's normal. We're not going to fly the nose cone by itself. But now I have a nose cone. And in fact, it says it's made out of polystyrene, and it even knows how heavy it is. But if you want to, you could potentially override the mass in the center of gravity. But I'm just going to leave it alone, assuming that the library knows pretty well what kind of nose cone this is. So, got it. I got a nose cone. Next thing I need is a body tube, an upper body tube. And notice it automatically drew the body tube to fit the nose cone and overlap the shoulder. That's good. I need an upper body tube that's made of blue tube. Let me see. Again, I'm just going to sort by diameters and look for 3-inch blue tube body tube. Here we go. There it is. There's a 3-inch diameter body tube. And it says, that's fine. If you buy it from the company, it'll be 48 inches long. It's like, okay, I don't really want it to be that long. So let me just reduce that. I'm going to reduce that to 18 inches. Is that right? I don't know. I did not measure it. You have a rocket, you can measure it yourself. But for starters, that will do. And then I'm going to click on body tube and say, here is something that is related to a child of this body tube, and that's a coupler. So I want a coupler that fits inside. So let me go looking for a coupler from a database. Again, I'm just going to find one that will fit inside of a 3-inch body tube made of blue tube, and there it is. Blue tube comes from Always Ready Rocketry, so that is in fact the right thing. And it turns out that it's 8 inches long. That looks okay, except it needs to stick out because right now it's all inside of the upper body tube. So I can drag it around, or I can type in. In fact, I want it to stick out halfway. So if it's 8 inches long, I think that is true, in fact. I'm going to make it stick out 4 inches. Fine. Next up, I need another body tube. This is my lower body tube. And let's find one. Again, I'm looking for that 3-inch blue tube. Where is it? There it is. Okay. 48 inches long. Again, I don't need it to be that long. I'm just going to make up 24 inches. Again, that may or may not be correct, but you can correct it if it's not correct. So, and since it knows that it's blue tube, vulcanized fiber, that's what they call it in this program, and hopefully they have the mass per unit length correct. Now, in that lower body tube, I need some details. For instance, I need some fins. I'm going to just go with trapezoidal fins. I'm not even going to freeform them the way Kelly was showing you. So in this trapezoidal fins, I can draw things that are longer, and I can draw things that are taller, and I can draw things that have more or less of a tip. Is that right? I don't know. It's not terrible. In fact, you could do better, and you should do better, but I'm just going to start with 3 fins that are this shape, and I'm going to say that they are made out of wood, maple, and I'm going to say that they are 0.25 inches thick. And I'm not going to bother trying to curve them or anything fancy.
Don't forget your fillets.
I'm not going to do fillets. I'm not going to do lots of details. But there is a place to do fillets. I'm not going to do them. On the other hand, I'm going to take a look at the back view and notice that I can look at the view of the rocket here. So in other words, there's different ways to see this rocket if you want to, some of which are more and some of which are less realistic. I'm going to do all my drawing from the side view where I can see inside. Notice that I have not put any end caps on my coupler tube. I have not put a forged eye bolt here. You can do all these things. I haven't put any parachutes in it yet. I better put at least one in a moment. Otherwise, it will crash when I try to fly it.
You also have a very important error, Dr. Flaten.
What's that?
You have a body discontinuity in diameter.
I don't know where that's coming from.
So I do all my measurements by hand.
I just told it to automatically fit the parts together, so I'm not sure why it's complaining.
Yeah, so one of them is 3.124 inches. If you click up on body tube up there, double click up on body tube.
This one?
Yeah, either of them. So your outer diameter is 3.124. Click on the other one. 3.124. And what is your nose cone? There you go.
Okay, so basically it pulled something out of a library that said 3.1 and pulled something also out of a library that said 3.124. I don't know if I can fix that or not. I guess I can fix that. This is just sort of a library difference of opinion from two different manufacturers. It's actually sort of important because it turns out that not all 3.1-inch nose cones fit. And so if you're buying Blue Tube, you might want to go to the Blue Tube company and see if they sell nose cones. Presumably they will fit Blue Tube. And if you go to a different company that doesn't sell Blue Tube, their nose cones might or might not fit. Okay, I do have to push on. Just give me a few more minutes, please. Not many, though. I'm going to put inside of this body tube an inner tube. I'm going to say that this inner tube is 38 millimeter in diameter. And that's good. I don't need it to be that long. This is going to be my motor mount tube. So let me just say maybe 12 inches long. I think yours is longer than that, actually. Maybe. And I'm going to... Where do I get to say that this is the motor mount tube? But that's when I choose the motor later, I think.
So go, nope, you're fine there. Go to the second tab up at the top that says motor.
Yep.
And
This is the motor mount. Yes, good. Thank
Yes.
you.
Mhm.
And I'm also going to name it motor mount tube.
I also made a comment in the chat, but I'm not sure every group sees that. For the nose cone, I would not recommend using polystyrene, as that's typically used for low power rocketry. We're going to want to use polypropylene as your nose cone material. It's going to have vastly different weights.
Fair enough. I chose from a library, and so maybe what you're
Yeah.
suggesting is also in the library. I'm going to make, I'm going to put on 2 centering rings here. Here we go. Make them 0.25. I'm going to make them out of wood. And I'm going to put one of them up toward the front here. And I'm going to make a second one. It won't complain if you don't do this, but this is realistic, so why not? Maple 0.25. And this one is staying at the back of the rocket. So I have 2 centering rings. Yours actually has 3. And notice that I'm not doing too well on my stability right now. Once I add a motor, I will do even worse on my stability because the motor will drag my mass toward the back. And right now my mass needs to be farther forward. Instead of adding mass up here, though, I'm just going to make my fins bigger. So I'm going to go back to the fins, edit the fins, and just make them a little bit taller. And notice, as I make them taller, it really sucks the center of pressure back toward the fins. And so hopefully your kit is fine, but I need bigger fins for this thing to actually work. Okay, that was pretty easy. I need to put in at least 1 parachute, and then I'm going to put in a motor and fly it, and then we'll be done for tonight. You need to finish this up with a second parachute, et cetera, et cetera. So let's say we're going to put the parachute, a drogue parachute, into the rear of this. So I'm going to choose something goes in the body tube, the rear body tube. Let me say that the parachute is 15 inches in diameter. I say that because that's the size I gave you. And I'm going to put this parachute down toward the bottom, right close to the motor. And the reason is that's where the parachute will in fact slump to. And I'm just making it sort of realistic in size. There's a parachute and it's down toward the base. And then I'm also in the body tube going to put a shock cord. The shock cord will be made out of tubular nylon. Let me try a 14 millimeter tubular nylon. Let me say that this is maybe about 15 feet long. Again, I think that's approximately what you will be doing. And I want that to be sort of down close to the parachute, and that also takes up some space in the body tube. I'll set it right above the parachute. It does fit barely. Yours might not be so tight. You can always type in here. Let me just type in 5.5. Perfect. Okay, and then here's one more thing I need to do with this. I better go back to the parachute and tell it, when is this parachute supposed to come out? Parachute, edit. When does it come out? At apogee. I could also have it come out on the way down, like at specific altitude, like 500 feet up. But I want this parachute, this is my drogue parachute, to come out at apogee. Now it's time for a motor. So it knows which is the motor mount tube. That's good. I will select a motor, and I'm going to select an H225 motor. That's fine. And notice, as soon as I select the motor, it will draw it and it will change my stability from 1.98, I can see that, down to 0.875. I'm going to live with that. I would like that to be bigger, but I'm in a rush right now. Let me simulate a flight. Flight simulation, new simulation. I'm going to leave the wind speed at just under 5 miles an hour. This is important. You need to know how long your launch rod or rail is, and 72 inches is correct, but you might not have that in your thing. I think I had to change that and force it to stick. So 72-inch launch rod, because it needs to be going a specific speed as it comes off the launch rod. Simulate and plot.
You can even
It's going to
change
show me altitude, vertical velocity, and vertical acceleration, all versus time. Yes, Kelly?
You can change the altitude to the field that we're going to be flying at.
I'm not going to, but you can. Yes, you can actually give a lot more details, including wind speed and including latitude, longitude, and all sorts of funky stuff. I'm going to add one more thing to my graph, though. I'm going to add lateral distance. This is how far it drifts. Okay. When I say plot, it draws one of these multi-plots. So this red color, I hope it's red, I'm colorblind, shows that this rocket will go to 2,100 feet or so. And then it will come down under a single parachute and it will land. And by the time it lands, it might be several hundred feet away from me. That's the drift. Here is the speed. It goes up to a fairly high speed. It's tricky to read the units. The speed units are over here, 550 feet per second. And it has an acceleration, and then the acceleration dies away pretty quickly, and the velocity dies away more slowly, but does die away. This is useful, but almost more useful, if I close that and close this, is this table. Velocity off the rod, I need this to be 45 feet per second or better. And so 82 feet per second, no problem. That's easy. It's getting over 2,000 feet. I saw that on the graph. Velocity at deployment of the parachute, it was hardly moving because it was just at the peak of the flight. So that I want to be close to 0, and it is. This is good. It took about 9 seconds after burnout for it to reach apogee. So that's okay. I need to grind my motor down to that number. This is a bad number. I want the thing to hit the ground going no faster than about 25 feet per second, and it's going almost 50 feet per second. This is why I need a main parachute. So if I were to put a main parachute in, I would stick it up here in the upper section, and I would tell it, let the main parachute come out at some specific altitude, like 500 feet above the ground or something like that. And then it would come down at this 48 feet per second for a while, and then when it reaches 500 feet, it would pull a bigger parachute. Yours, I believe, is a 45-inch parachute. That's what I gave you. Hopefully that was appropriate. So the last thing I'm going to say here is I missed a bunch of details. And for instance, one detail I missed, so this is a tree of parts, and the parts aren't all here. One thing I missed is I missed the fact that there's going to be a bunch of avionics inside the coupler tube. Okay, and so you might just do that as a mass object, like 6 ounces, 8 ounces, something like that, inside the coupler tube. I also missed the end plates of the coupler tube. I also missed the upper parachute and its recovery harness. So there's lots of more details. And so this is definitely not done, but it's also possible to, well, you can spend all the time you want to. And so I would suggest at least add an upper parachute, an upper harness, and end plates on the coupler tube, and perhaps forged eye bolts at the appropriate places. Each of those is about 1 ounce. You should measure them. You have them in hand. Actually, yours might already be attached to things. And a third centering ring, and make the fins more appropriately sized based on your model, and make the length of this rocket more appropriate based on your model. I just guessed at what the sizes were, and I did not guess right. I'll tell you right now, the rocket does not look like this, but it's sort of along these lines. So we would like you to, this is essentially your homework. Hopefully it's in the homework slide. I'll go check. Work on your model and turn it in. Turn it back in. Show us what you've done, and add additional parts and run some simulations and see how it flies. And make sure that it comes off the rail at a reasonable rate and lands at a reasonable rate. And how high it goes is an interesting number, but there's no exact rule about you can't go higher than yay and such, or you must go higher than yay and such. But this is what a simulation program can do for you.
I'm
going to save this, just a second. I'm going to save this as basic blues draft. This is definitely not the real thing. I will post the basic blues draft. So everybody gets to start with this, but you need to fix this up and make it more realistic. Go ahead, Kelly.
So can you go ahead and change that parachute to 25 inches and show them what ends up happening in the simulation when you have equipment that does not work?
I'm sorry, this parachute?
Yep. Change that to 25 inches or so.
Okay, so right now it's at 15 inches. So you're
Oh, no,
making
then change it to like 7 inches.
fine.
And when you run it, you should get an error when you go back into flight simulations and you do.
It'll come down faster, but I don't think it'll give you an error, will it?
It might give you, well, when you have 2 parachutes, it definitely will give you an error if you're coming down too quickly from, if your drogue chute is too small, you'll get an exclamation point saying that you are popping a chute at much too faster rate. Nope, that one's perfectly fine. But if you look, yeah, 100 feet per second into the ground.
Right. So the idea is if you're coming down at 100 feet per second and then you pull a bigger parachute, you could easily shred it and it may well complain about that. It's like, this does not sound prudent. Okay. But yes, indeed. Watch this. If I go to the parachute, one thing for fun, edit, and say, this parachute is not going to come out at all. Now let me simulate that flight. New simulation, simulated plot. I don't understand that at all. I was expecting it would be totally parabolic. Something strange just happened to me. I should have tried this beforehand, but anyway, here's an example where I think the simulation is wrong. Basically, if I don't pull a parachute at all, I think I know what it did. This is interesting. It knows that there's a motor, eject. And so the motor eject went off well after apogee, because I reached apogee here at 9-10 seconds, and the motor eject went off at about 15 seconds. And after that, it said, you're coming down with a rocket that's at least in pieces. You may not have a parachute, but this rocket is not very aerodynamic. And so it's going to calculate the fact that I slowed down. You should not do this. This is called drogueless descent, where you come down based on a broken rocket, even with no parachute. I didn't realize Open Rocket would do that. I was thinking if I said no parachute, it would let the rocket stay together. No ejection charge, but apparently it fires the ejection charge and assumes the rocket breaks and becomes less aerodynamic.
And you can play
fair
with
enough.
that. You can change the motor ejection timing. So if you really wanted to, you see what that looked like, guys, you could just set the motor ejection time for like 25 seconds and it would set off after it's slammed into the ground.
So here's the delay charge. Can you actually increase that beyond 14?
I don't know. I've not really tried, but I'm assuming you can.
I don't know. So I changed the motor to say 25 seconds. Just for fun. What? No, I think it knows that this motor has a 14-second ejection charge and it will explode at that point. On the other hand, it's possible you might be able to turn off the motor eject altogether. You could also use a motor that doesn't have a motor eject. It's called a plugged motor. But we're over time. We should let people go. Thank you.
Before people head out, I know the build parts are really, really fun and the timeline isn't necessarily as fun, but that lets us know that you know exactly what parts go where, and it's kind of a pre-warning to us to make sure that things aren't getting built that are irreversible. So if you guys are still hanging out there with your build timelines, I could really use them. I have only gotten them from a quarter of the teams.
Have you been watching? So we are done, but you're welcome to continue asking questions. On the other hand, Kelly, I see that you've been monitoring and responding to the chat. I appreciate that. So if anybody put something in the chat and didn't bring it up orally, although I would prefer orally, frankly, we'll try to get back to you about that on the spot. But any other questions right now?
When you were building the rocket and making that coupler piece, you didn't have like the sleeve like the one model that we have. Is that going to factor in?
She does have it on there. It's not painted a different color, so it's a little bit hard to see it.
You can see.
I meant in the simulator, like how do you build that in the simulator? Because wouldn't that factor into it?
Okay, fair enough.
I can pull that up if you want. I've still got that going on my end.
So Kelly showed in a different model the fact that she built a model that had an airframe piece, and then inside the airframe, it was centered, a short airframe piece, and it was centered on a coupler tube, and then the other pieces attached to it. So yes, that's a detail, and maybe a somewhat important detail, because it does make your rocket longer. If you were to saw off part of your airframe and use that to make a switch band, then the rocket is the same length. But if you actually, and in this case, I did it, I gave you a switch band and you added it, so it did make your rocket longer by the length of the switch band.
Okay, I just didn't see where the switch band button was. I just saw the coupler and like the add new components. So I just wasn't sure how to do the switch band.
So the way that I did it is I actually I took a body tube and turned that into my switch band. And then I took the coupler tube and I built that underneath. So you can see that the coupler tube is centered on the switch band, and then everything else that goes inside. And you can see they're highlighting on the thing down there on the picture. So I built it all into there.
Okay, can you rename the parts kind of like in SolidWorks?
Yeah, so like if I want to call this 7-inch plywood avionics bulk plate, I can do that and it'll just automatically update there. And if you hit Control Z, just like you would Control Y and Control Z, you can see it's switching it back and forth. So Control Z works by backing out your last change in case you change something you don't want to. You can always hit Control Z.
And notice that next to some of the components on this model, at least, there's a little anvil symbol. That means this particular piece has an override. So in other words, if you measured the weight or the mass, and you know it is exactly 3 ounces in weight, you can type in 3 ounces, even though I didn't, from the library, guess it was going to be 3 ounces. You can even do an override for the whole rocket. It's like, just forget about all the individual components. This is a 32-ounce rocket, end of story. You can type that in and completely override the individual part masses, but I don't recommend that. I think it's good to use the part masses and maybe even measure the part masses to confirm them.
This one was the particular case where we measured everything out because it was a Mach 1 supersonic rocket. So it was much more important for us to have these like tied down completely and knowing exactly what specific everything is. But for our rocket build, the basic blues, it's not going to be nearly as important.
Kelly, go to the top of this tree. Go back to that and go to the top of the tree. I want to show one thing. All the way to the top. And then click on stage. And say edit. Yeah, so the idea is you can override both the center of gravity. That would be based on balancing it with your finger, perhaps not with a motor in it. And then you can override the mass. So if you know the final mass and the exact balance point, you can actually just type in both answers there and not have it guess or estimate either one.
And you can see how that shifts down there on the diagram.
Yeah, so I see that it's moving at a couple inches perhaps. And so it's like, it thought it was going to be here, but in fact, we know it's not, it's here.
Yeah, you basically take everything in here with a grain of salt. It's a free program and it doesn't necessarily, when I weighed the nose cone out and I come up with an overall weight of 5.36 ounces, that weight is not distributed over the whole thing. It's just kind of a center mass weight. And so it can be very hard for this to understand how that mass is actually, working across the whole thing. So this was originally 5.74 and now it's 5.36. So just different things with that. What I was talking about earlier with the parachute is if you go into here and you change your parachute to something and you change your drogue to things that are not going to work, when you go and run your flight simulation, you're going to get a little warning here, and it's going to tell you recovery device deployment at high speed. And you can see that second warning. Don't worry about the first one. It's a supersonic thing. But the second one is 77.9 feet per second, which means that when your main parachute comes out, it's going too fast and could very well rip that parachute straight out.
Okay, so apparently it has a rule of thumb about what is too fast. My rule of thumb is landing. I think the actual technical number changed from 25 feet per second to 35 feet per second for Tripoli clubs recently, as in a couple of years ago. I still like 25 feet per second, but this is another rule of thumb is don't be going faster than 50 feet per second when you pull a parachute or something like that. Apparently 77 feet per second is considered, by this program at least, asking for trouble.
And 966 feet per second is definitely not good either.
Okay. Anybody else who's still on the line? Any more questions?
I have a question about the skid for the avionics bay.
The
Okay.
sled.
The sled, excuse me. Yeah.
Go ahead.
If when we make or we design the sled, can we create the sled to have like a tab and kind of notch out the end cap so it's a little more rigid and not so loose on the
It would be a good
rails?
idea if the sled did not wiggle. That's true. And so one way to do that is to make the sled length the same length as your coupler tube with caps on it. But if you do that, then you might start to interfere with the nuts, right? The nuts from the eye bolts. So that's why Kelly notched out for the nuts. But yes, indeed, it's a good idea that it doesn't wiggle, and there's a variety of ways to do that, including adding extra nuts to hold it in place at a very specific location along the threaded rod. That's another possibility.
One thing I have to say about that is if you look here at the holes right there, like you can see how close they are to the sled itself. If you're gonna do that, you need to make sure that if you're gonna go like all the way up against the bulk plate, that the nuts are flat, like the top of them on top of like the tightened part of the all thread is nice and flat on top, so that sits directly on top of that. So your nut, and then this sits like this. Don't have it angled, otherwise it's gonna bump up against that.
You will find out the hard way that sometimes it looks good on paper and you can't actually do it that way.
Yeah, because I just was gonna use like an example from like a previous, so they have kind of like what we were gonna do was do with like wood and then just have like tabs that go down and like sit on it. But as you see, they kind of have like a standoff that goes into the lid, I guess was what I was asking about.
That's, I mean, it's definitely, it's a little more work than really is necessary. But if you want to do it, you definitely can.
So it turns out, Lauren, that it's a good idea, but not the only way to approach it, to have the sled the right length from the get-go. On the other hand, if your sled happens to be short for any reason, including that you wanted it to be shorter, then what you can do is you can put nuts onto the threaded rod and just screw them down until they hit the sled. And then it's the nuts that hold it from shaking, as opposed to the end plates that hold it from wiggling around.
Okay, and would it be a smart idea to also weigh I guess the whole sled with the assembly?
You have to. It's not a
And
good
then-
idea. It's a required
Okay.
idea.
Okay, I
You
just
can't
wasn't
do
sure.
that. You can't do that yet because you haven't actually built it and put all the parts on it yet. But yes, that will be coming up. You will definitely want to be realistic in your model with how much avionics you put in there.
Okay, I just wasn't sure if you guys were intending on us self-designing it or having like an ECAD file of like a 3D print design or something.
We're going to tell you what has to be on it. You're going to have to figure out how to make it. And if you have old rockets, you can look at what other people decided, but we're not going to insist on anything other than it has to work, and we'll tell you the functionality.
So part of that is, for instance, he gives you this battery tray, but I've got a custom printed 3D battery tray right here. So you need a battery tray. What battery tray you use is up to your own artistic, talents. You need to have your sled. How you design your sled is up to you, but it needs to have everything on it.
Okay.
Sometimes I build sleds such that there's enough space between the threaded rods that you can mount batteries and altimeters in between the threaded rods. In other words, on the bottom of the sled. That just leaves the top of the sled for other things like more electronics or sensor suites or whatever. And so Kelly put her stuff on the normal side of the sled, but in actuality, I think the spacing between the threaded rods is large enough that you could potentially put your altimeter and maybe even your 9-volt battery on the back side if you wanted to, especially if you were preserving the top side for something even cooler.
And also our fiberglass rocket, the supersonic, we needed to actually have 2 sets of electronics fully on there. So we needed to use the top and the bottom. So the middle was actually where all the wires ran through between the two rails, and it had the two rails going through it, and then the top had one set of electronics and the bottom had a different set of electronics. So it just depends on your needs and how much room you've got available.
Yeah, that was my question too, was whether or not with all the electronics being on like technically like further on like the center of gravity or whatever on one side, if that actually affected it or not.
You know, slightly, but we're not too overly concerned about, like, you could, if you really wanted to, you could do the calculations of how the two motor retention washers and standoffs, you know, they're offset from the center, but these are all just like moments of, you know, like, I don't know if you've taken statics, but those are just moments that you would create about that. And the total overall moment, like the sum of all moments for that, is such a small difference off of the you know, the axial line of the rocket, that we're not too concerned about them for this stuff. On top of that, because of the static margin that you create with the rocket, as it's going up, it has no interest in leaning from one side to the other because of the sheer amount of wind going across the thing and the drag keeping it pretty much vertical.
Okay, yeah, I was thinking of the statics of it, so that answered my question.
We'll give you lots more details next week about the wiring, but it's true, the wires themselves don't change much because they're so lightweight, but the battery is a chunky thing, and where you put the battery within the av bay could potentially affect its overall balance point. Of course, it will have a specific weight, that's true, but you could imagine if you take that weight and put it at the top or take that weight and put it at the bottom, that would make a slight difference. So when you add in your model, here's my av bay and it's 6 ounces. I'm just making that up, but if that's true, you might even try to be more realistic and say, and it's 6 ounces, and I know that it's a little bit below the center line of the av bay.
So the nice part about this one is that the rails are actually low down. They're below the axial line. So when you put your rail on,
Your sled.
yeah, you put the sled on the rails, you'll notice the battery doesn't sit too terribly high above the center point. In fact, part of the battery is going through the axial line. So it's not as bad as it could be, because some of these have it directly in the middle, and then your battery is going to be even higher up potentially.
So I told the guy who drilled those holes for me, why don't you set it up so the sled could potentially be right on the line, right on the midpoint. But if that's the case, then the components that are on the sled sort of by definition will be high, shall we say. But you're right, it's, quote, not too bad. I would agree with that.
Yeah, you just want to end up with something kind of like this. And you'll notice there's a standoff on this side between the, you know, that's where I put my wing nuts to make up the slight difference. I didn't want it to be from end cap to end cap. I wanted to be able to adjust that slightly, but this is tight. It's not going to move around on me. So this will do exactly what it needs to do properly.
On the other hand, is it tight when it's in the coupler tube?
It certainly is.
Okay, that's more important. Anybody can be tight when you don't have a coupler tube, but add the coupler tube and then now it's loose. That would be a bad day.
Yeah, that's what the two wing nuts are for, so I can adjust where this board is going to be in here, and as compared to where the two bulk plates are going to be.
Okay, cool. Anything else?
I think we've exhaustively covered it. I do have to talk to you for a second after this, if that's all right.
That's fine. Let me just stop this recording.